Hi everyone, welcome to my presentation, Data in the Wind, Evaluating Multiple Encoding Design for Particle Motion Visualizations. Data visualizations usually leverage channels to encode data values, such as color, position, length. They are all static channels. Meanwhile, the application of motion is very limited. People use motion to make animated transitions from one visualization state to another. So, this animation do not encode any data values. However, particle wind flow map is different. In this example, it not only uses color hue, length, and angle as encoding channels to encode wind data, but also use movement as a main channel to encode wind speed. Here is another example from HintFM. It has a minimal design style to visualize wind data by using both static channels and motion channels. This is the canonical ranking of effectiveness of common data encoding channels. As we can see, motion does not even belong to the magnitude channels, which means we usually do not use motion to encode numerical data values. But particle wind flow map does use motion to encode wind speed data, which makes it unique. In this study, we want to model how well people can judge differences in particle motion maps in two conditions: motion-only condition and the motion paired with other static channel condition. A natural way to model this is to investigate the accuracy of people's judgment. However, motion do not compete bandwidth with other static channels. Indeed, motion increases the bandwidth of the visualization interface. So, we are more interested in how reliable people can retrieve information from particle wind flow maps at different speed levels. To measure this, we will use the JND as the unit, just the noticeable differences. Here's a simple example to demonstrate the idea of JND. Can you tell which circle is larger? I guess it is very difficult for most of people, because the radius difference is only 1 pixel. It is too difficult to tell. How about this new pair? It is much easier to tell the right side circle is larger, because the radius difference is 10 pixels. So 10 pixels is a noticeable difference. And how about this new pair? If you can tell the differences of the circles of this new pair, your JND will be between 1 pixel and 5 pixel, and if not, your JND will be between 5 pixel and 10 pixel. Let's move to the experiment design part. We choose HintFM as our template visualization due to its minimum design. We simplify the stimuli from hint.fm, remove background maps, and construct a straight stream stimuli in two conditions. The motion-only encoding condition, also called the single encoding condition. The speed value only encoded by motion without any other static channels. Another condition is the mixed encoding condition. The data value are encoded by motion and the three most common static channels in particle wind flow map: length, color saturation, and density. In each trial, there will be two stimuli displayed side by side. One use base value and another one use the compare value. The idea of the staircase procedure is simple. If participants give us correct answer, the next trial will be harder. And if they give us a wrong answer, the next trial will be easier. As you can see, all compare value is smaller than the base value, so we call this a below direction. And here is above direction. The compare value is always larger than the base value. Here's a demo of a participant taking the experiment. Participants could select answers by clicking on the stimuli and proceed to the next trial. Here is the experiment parameters. We have 6 base values measured from HintFM, 2 directions, and for each base value and direction combination, there will be 25 trials. We call it stair length. In addition, each participants are assigned to either mixed encoding condition or single encoding condition. So make it a between subject design. Here is a screenshot of stimuli in each speed level from 20 pixels per second to 120 pixels per second. In mixed encoding condition, you can still tell the difference by static channels such as density. In single encoding condition, all stimuli look the same in screenshot. After launching it in Prolific, we got 23 valid participants in mixed encoding condition and 21 in single encoding condition. To calculate the JND value, follow the previous methodology. At each speed level and each direction, we calculate the average of the second half of compare value as JND value. Because we have two directions at each speed level, there are two sets of data for each speed. To fit the linear regression model, we move the data in above and below direction to opposite directions by this equation. As you can see, for all data in above direction, they will be moved towards larger side at x-axis, and for below direction, they will be moved towards smaller side. After the adjustment, we can fit linear regression model to the dataset. Here is a model result. As we can see, the mixed encoding performance are better than the single encoding performance at each speed level. Then, the JND value appears to be linear increase as the speed rise within the on-screen speed range. That's the end of our modeling part. There are a couple of limitations of this study. First, we only cover two conditions, motion only and mixed encoding condition. Second, due to the length of the experiment, we made it a between subject design. Third, we did not compare the motion only condition and the static channel only condition. In the future, there are a lot of opportunities to explore this direction. For example, we can explore which static channel have the best performance paired with motion channel, or we can also explore the effectiveness of other designs of different particle motion flow maps. That's all for this presentation. Here is a QR code link to our supplementary materials in OSF. Thank you very much.